for many real problems. I'm missing cables here. Okay. And we will start with Professor Wayne Luke from Imperial College. When I switch on my computer. Okay.
Hello, good afternoon. It's a great pleasure to be here. So Oscar gave a very lucid and hopefully you find attractive description of how spatial programming can be very exciting. So what I'll do is simply to provide a few personal perspectives and end with some challenges, just in case there are some PhD students here who are looking for PhD topics. To try to have some challenges to meet. So the first is something that I find very exciting, and that is actually a European project, an FP7 project in developing the next generation of self-aware systems. Now actually, this particular outcome was not described in the original project plan because it was, as you would expect, in some of the most exciting research, it gradually occurred that we could actually do this, that our technique for spatial programming can actually be used for the design of the next generation of smart airplane. So this is a collaboration with Airbus as part of the FP7 EPICS project. And the idea is that we want to be able to monitor the instruments of an airplane because as you can imagine that when it is 40,000 feet up, sometimes it might be got frozen, sometimes the pressure might get too much, sometimes there might be volcano ash and ashes and so on. So the reading from the instruments may not always be believable. Now the problem facing the pilot is that there are many, many instruments around, and some of them might be correct, some of them might not be correct. And within a split second, you need to decide which one do you need to believe. That's not so easy. Although sometimes you could blame people afterwards, one needs to imagine that they really have to have very professional training to decide which are correct, which are not correct. What we hope to do is to be able to help them so that in the next generation of smart planes, we'll be able to monitor the output so that we could look at the, for example, the statistical properties so that if the mean or variance of the reading are behaving in an impossible way, then there would be some warning to the pilot to say that, well, maybe you probably should not believe this particular set of readings and so on. Okay, so what we've developed is a very effective way of monitoring the output of any instrument, in particular monitoring the statistical properties, computing that in real time. So there is the standard data path computing whatever that the instrument needs to compute. And then this is included as an assertion, but in this case it's not a functional assertion, it is a statistical assertion in order to fit the reading into an adaptive engine in order to produce the appropriate output for the pilot and so on. So, as I said before, this is something which was not expected in the original project description, and we are very delighted that it works so well. The second example is also related to statistics. But in this case, that when we have spatial programming, then we have a lot more freedom than the traditional time-based computing. Because we could now vary the representation so that part of the time it could be computing at a, for example, at a lower precision, and then later on, when we need to get into a high precision phase, then we could change representation in order to now have a more accurate representation. So here's an example that we developed for Monte Carlo calculation, that we find that in most of the computation, we can actually compute at a low precision phase. And we calculate the result over here, but in order to get the final correct result, then the last few percentage of the computation could then take place in a high precision. So one could see that there are optimization for spatial programming that might not have the corresponding version in the normal computation. So the challenge is how to actually understand and eventually automate this kind of optimizations. And my last example is when we talk about try to make FPGA to be friendly to software designers. Well, perhaps the best way is can we actually generate the actual computation system, both hardware and software, all automatically? Well, trying to do that generally would probably be not so easy. But I think for specific application, that would actually be achievable. So Oscar gave an example of MaxGen FP, as you remember. We also have another example for generating sequential Monte Carlo engines. And we demonstrate that the same engine can be automatically generated and customized for different applications, such as those in finance, in robotics, and even in air traffic management. So there is a paper for this year's FCCM conference, and some of the software templates that generate these different applications are actually now online, and we could actually go in there and try it out yourself. So there are various interesting examples for spatial computing, but I should not give you the impression that everything is so rosy that there is not much more to do. Well, you can imagine that there are actually still quite a lot of research in order to fulfill the full potential of spatial computing and spatial programming. So, for example, I mentioned we could generate Monte Carlo engines, but how about other common applications? So can we generate other, for example, other stencil computation generator with different stencil patterns? And also, I describe optimization for data representation, but there is only one particular kind of optimization. In general, there are vertical optimizations as well as horizontal optimizations. How can we automate the composition and customization of all such optimizations? And of course, we know even the best programmers make mistakes. How can we find ways of locating such mistakes, but allowing the designer to still program at the high level? And as well know that we are gradually moving a lot to cloud computing, and spatial programming itself can also be moved to cloud computing, as you can imagine that some of the data centers and so on supporting cloud computing could actually benefit from some of the data flow engines and so on. But how to distribute tasks and how to schedule the tasks and so on while maintaining the quality of service expected from the users. And finally, as we know that OpenSPL is an open standard, would it be attractive if eventually we would be able to generalize and extend this standard to cover both the design of hardware and software and so on? Okay, great. Thank you very much.
Thank you very much.